Hello everyone. These are the notes for section 4.7 part 2. We are still talking about the law of conservation of momentum, and today we are going to talk about elastic collisions, and we'll define exactly what that is a little bit later on. So let's go ahead and do our review here. Momentum, remember momentum is a quality of motion. So that definition has now been on 2 sets of notes and some video questions, maybe 3 sets of notes. So that's going to be an important one, right? And here's our momentum formula. So P, right? P is momentum, mass times velocity, and the units that we use for that are kilograms times meters per second, because it's mass times velocity. So kilograms times meters per second. Our law of conservation of momentum says that the momentum of a closed, isolated system remains constant. Right? And last time we looked at what happened when 2 cards started out opposite from each other and ran into each other and stuck together, and we saw that their momentum before they collided was equal to their momentum after they collided. Similar thing today. So in elastic collisions, that's what we talked about last time. 2 objects that collide. Collide have 2 L's? I think it does. And stick together in, elastic collisions. So as you might expect, this is the opposite. So we have 2 objects that collide and then separate. And I always think about playing pool or billiards, right? When you use the cue and you tap the ball and it taps into another ball and they don't stick together, right? That would make pool really boring. They bounce off of each other. So 2 objects that collide and separate, those are elastic collisions. So remember the way that we do this to find the momentum of a system, we're going to add the momentum of each part of the system. So our systems are going to continue to have 2 parts to them, and we're going to calculate the momentum of each part, and then we add it together, and that tells us the momentum of the whole system. So here's our carts again, and we're starting with cart 1, which is the red one, and cart 2, which is the blue one. And again, we have a mass for each cart. We have a velocity for each cart. I do want to point out to you, this time we have a negative velocity, right? So we know that the red cart is going to travel in the positive direction and the blue cart is going to travel in the negative direction. So those negatives are really important. Okay, so let's write down what we know. Mass of cart 1, that's the red cart, 1 kilogram. Velocity of cart 1, 5 meters per second. Mass of cart 2, also 1 kilogram. Velocity of cart 2, negative 1 meter per second. That's what we know. Direction's important. Okay, here's our formula. We've written this down once before. It's always good to write things again. So the total momentum is going to be the mass of cart 1 and the initial velocity of cart 1 plus the mass of cart 2 and the initial velocity of cart 2. And in our example system here, our total momentum is going to be 1 kilogram times 5 meters per second plus 1 kilogram times negative 1 meters per second. So if I do my math correctly here, I'm going to have 5 plus a negative 1, which is going to give me 4 kilogram meters per second. Everybody okay with that? See where all those numbers came from? All right, these carts are going to collide with each other and then separate. One more time, that's called an elastic collision. right? When they collide and separate. So our carts now look like this. So the part you couldn't see was the collision. It was hard for me to take a picture of that part. And so we can see that their masses haven't changed. They're both still 1 kilogram, but now their velocities are different. Cart 1 is now heading in the negative direction, and cart 2 is now heading in the positive direction. So they have switched directions from where we started up above. Right? So things to notice. All right, so let's write down what we know. We have the mass of cart 1, which is still 1 kilogram. And the velocity of cart 1 is now negative 1 meters per second, so it changed direction. Mass of cart 2, also 1 kilogram. Velocity of cart 2, now 5 meters per second in the positive direction, so it also changed direction. So here's our formula for the momentum of our system after the elastic collision. Whoop, typo. Ooh, elastic collision. All right, so we're going to say our total momentum is m1 times final velocity plus m2 times final velocity. So in the first time we did this, we had those carts stuck together, so we added their masses and there was just 1 velocity. Now the carts are not stuck together, so we still have 2 separate carts, and so we have our mass and velocity of cart 1 and our mass and final velocity of cart 2. For our example system, we have our total momentum is going to be 1 kilogram for the mass times negative 1 meter per second for the velocity plus 1 kilogram for the mass times 5 for the velocity. And so my total momentum, negative 1, that doesn't look like a 1, does it? Negative 1 plus 5 gives me 4 kilogram meters per second. So if we're paying attention, we have, before the collision we had 4 kilogram meters per second. After the collision we also had 4 kilogram meters per second. But the velocity changed, right? The velocity went up for 1 cart and changed direction, went down for 1 cart, changed direction. So our velocity is changing, but our total momentum is staying the same. All right. So just like we did before, let's just make sure, does this support the law of conservation of momentum? Is my momentum before the collision equal to my momentum after the collision? Talk it over with your table partner for a second there. Go ahead and write down the data that shows you whether or not that statement is true. All right, hopefully you wrote yes. Our momentum before the collision was 4 kilogram meters per second. Our momentum after the collision, also 4 kilogram meters per second, even though the velocities of those carts and the direction of those carts shifted. So this time we're going to put both of the parts of our formula together. We're going to have the mass and the initial velocity of cart 1, or object 1, plus the mass and initial velocity of our second object is equal to the mass and final velocity of our first object, the mass and final velocity of our second object. So here is before the collision, and here is after the collision. Now, if you remember from last time, that before section, that all looks exactly the same, right? The only change we've really made is in the after section. All right, this means we're going to have to read our problems pretty carefully. So let's take a quick look at our example problem here. I almost forgot. Let's pause, and if you need to go get a calculator, please do that. So get up and get yourself a calculator if you need one. All right. No, I've already used purple. How about pink? Okay, so let's do our example problem here. And again, before I write anything down, I'm going to take a look at what I'm dealing with. So here I have 2 carts. I've got cart 1, the red cart. I've got cart 2, the blue cart. We're going to assume that they hit each other All right, and once we get over here and we're looking, we still have our red cart, cart 1, our blue cart, cart 2, and we really don't know at this point, but just because this is what we're working on right now, we can assume that these two carts were moving toward each other to start with, and now they're moving apart from each other. All right, when we read the problem, we'll know for sure. So, lab cart 1, that's the red one, has a mass of 15 kilograms and an initial velocity of 1.5 meters per second. Okay, so that's my red cart. And then my lab cart 2, that's the blue one. I kind of ran out of room. Let's do it over here. Has a mass of 12 kilograms and is traveling to the left at negative 2 meters per second. So negative 2 meters per second, right? The opposite direction. So that's my blue cart. Lab cart 1 hits lab cart 2 and they separate. So I've got an elastic collision here. After the collision, lab cart 1 has a velocity of negative 8. So there's my VF is negative 0.80 meters per second. And I would like to know the velocity, the final velocity of cart 2. That's what I don't know. So if we write out our formula, let's see, I'm going to give myself a little bit more space here. So I have M1 V initial for the red cart plus M2 V initial for the blue cart is equal to M1 final velocity of the red cart plus M2 final velocity of the blue cart. So this is going to be 15 times 1.5 plus 12 times negative 2. And then my mass didn't change, so that's still 15 times negative 0.80 plus 12. And there's what I don't know at the very end. Now, just be careful, all right? When you get all these numbers and all these letters in here, make sure you have something left to solve for, right? I got to have a variable here instead of a number, so I have something to solve for. So let's go ahead and do this math. 15 times 1.5 gives me 22.5. 12 times negative 2 is negative 24. You're using your calculator, right? You're not just copying. Okay, and then on this side, I've got 15 times negative 0.8, which is 1.2. And there's my 12 VF, so that's still what I'm solving for. So I'm going to keep going here. 22.5 plus negative 24, negative 1.5. You're using your calculator, right? Equals 1.2 plus 12 VF. Now I have some more steps here than I did before. I have to subtract the 1.2 from both sides. That gives me negative 2.7 equals 12 VF. Right, and the reason I know I have to subtract that is because there's this plus sign right here. That tells me I'm going to subtract. In this step, there's no plus sign left, so now I'm going to divide both sides by 12. Totally out of room. Okay, so now I've got, what do I have? Negative 2.7 over 12 is equal to VF. Right, my 12s cancel. All right, if you plug this in your calculator, you're going to get VF equals negative 0.125. Let's see, significant digits, I can have 2, so this is going to be negative 0.13 meters per second. All right, let's take a quick look here. Is this what I expected to have happen? So they were moving toward each other, right? This was 1.5 in the positive direction, and this was negative 2. All right, so they're moving toward each other. And then afterwards, this was negative 0.80 meters per second. And this is negative 0.125. So they did separate, but this one is also moving in the negative direction. It just slowed down. Okay, interesting. So here's our answer, 0.13. So just like I did last time, I'm going to go ahead and put the answers for the practice problems here. I'd like you to do at least one of these before you jump into the second part of the lab. All right, so practice problem number 1. The correct answer is 0.931 meters per second in the positive direction. And for practice problem 2, we've got a final velocity of 6.28 meters per second, also in the negative direction. Work with your partner. Do at least one of those, please, before you start the lab. And again, the teacher's notes have all of the work in them, so if you get stuck, feel free to ask to see those teacher's notes. All right, thank you very much.